Welcome to the lecture series on the exciting field of condensed matter physics. I call this as exciting field because we are dealing with electrons. We are dealing with electrons in metals and semiconductors, insulators and so on. Without electrons, there will be no electronics. Without electronics, we will not have computer, we will not have cell phone and so on. Therefore, the quantum computation and so on, as I told you in the first lecture, multidisciplinary field encompassing several areas, right. Therefore, from biological materials, geological materials and so on. And in this lecture, before we go into the details, go back to what I did in the previous lecture, recapitulate some of the important points, right, so that the continuity is maintained. We discussed the problem of a particle in a one dimensional box. You see the one dimensions, it is a one dimensional box. Now, what do we do with this? What is meant by a particle in a one dimensional box? The electron bound to an atom or a molecule or a one dimensional metal, and this is what we call as a particle in the electron confined to a one dimensional metal, wherein the important thing is, I underline this, is a constant potential. As long as the electron is there in the well, you know what is a well? We have well in the house, the well is well, right. You have water in the well, water cannot come out, right, you have to do work. Similarly, the electron in the atom or in a metal will not come out of its own, right. Now, here is the infinite potential, the potential goes to infinity, the electron cannot escape from the metal, this is a one dimensional metal, right. The one dimensional metal extends from x equal to 0 to x equal to L, the length of the metal is L, and inside this box the potential is assumed to be 0, 0 is a constant, that is the reason why it is called constant potential. I emphasize the word constant potential because in the days to come we will come across periodic potential. Maybe in a few minutes I will come across the periodic potential problem, and the periodic potential problem only gave the distinction between a metal, semiconductor and so on. So, that is the reason why I emphasize constant potential, and one more term I will be making use of, I will come to that later. Those things are important, keep this these things in mind. Okay. Now, from the one dimensional box, what do we get? We get the eigenvalue. If when you use the Schrodinger equation, because you are dealing with electrons, you have to necessarily use the Schrodinger equation, and when you solve the Schrodinger equation, you will get two things. One is the eigenvalue or the energy value, and the other is the eigenfunction, right. The energy value E will be given as h bar square k square by 2 m, right. Unlike the electron in an atom, in the electron in the atom was given in the Bohr atom model as in terms of n, the principal quantum number. Now, the principal quantum number that was used very well in Bohr model is no longer valid, because the electron is moving here and there, right, and like gas molecules roughly speaking, right. Therefore, your E is related to k, right. H bar cannot be changed, is a constant, Planck's constant. M is the mass of the electron. Therefore, the only variable is k. Now, therefore, this is a very well known Sommerfeld free electron parabola. What does this give? It gives you a relation connecting energy and h bar k. H bar k is the momentum of the electron, okay. The momentum in the energy momentum relation. Throughout the lectures to come, we will be talking about the energy momentum relations, right. The energy momentum relations, which will be complicated, right, which will be very much complicated in the lectures to come. So, essentially what is your k? K is 2 pi by lambda, lambda comes in the denominator. Therefore, your k will be 2 pi by lambda, lambda comes in the denominator. Therefore, k will be a vector in reciprocal space, that should be remembered, or a direction or a point in the Brillouin zone. I will come to those things a little later. Now, the question that we ask, given the momentum k, this value, what is the energy? The only thing that you can do is you have got k here, what is the energy value? If the k has got this value, what is the energy, right? The energies are discrete, the energies are not continuous. In a classical well, in a well in the house, water is there, water does not stay in sheets, whereas the electron will be in well defined energy states. Your n is equal to 1, k shell, L shell, M shell and so on in the atomic case. Similarly, in the case of solids, you will be having k is the quantum number, n is not a good quantum number, it is replaced by k, k is the quantum number. So, you ask the question, given the value of k or given the momentum of the electron, then what will be the energy. Therefore, that is the Sommerfeld's free electron parabola, and you will see a very exciting thing, how this parabola is changed when you go to a periodic potential. What is when we periodic potential? I will come to that later. And when you go to periodic potential, how does the free electron parabola changes, right? I mean that we will see. The eigenvalues and eigenfunctions which I have been mentioning is given as I showed in the last picture, and also your E will be can also be written as n square h bar square pi square by 2 m L square, and n is a number, a positive integer, n is a positive integer, and it should be noted that the energy eigenvalues are quantized, right. All the things that you have got here, L is the length of the box, m is the mass of the electron, and h bar, and now they are all constants. Therefore, one is what I would like to tell you is the energy is quantized, right. N is the n will take positive integers 1, 2, 3 and so on, the quantized energy values. Okay. It should be noted that this is the eigenvalue. The eigen function, as I told you, is a sine function, right. Sine function is a plane wave, or a sine function plus cos function, or e power I k x is a plane wave. The example of a plane wave is the light wave that you have got here, is the electromagnetic spectrum, and this light wave is an example of a plane wave, right. Now, these things are to be kept in mind, because I will be using plane wave, or I will be talking about augmented plane wave. I will come at a higher level, days to come I will go to those lectures, I will be talking about augmented plane wave method. Now, therefore, a plane wave is that is you have a spherical wave front, right. Here is a plane wave front, the plane wave front, that is when the light is propagated, as I told you, when in the electromagnetic spectrum the light is propagated, and the wavelet or the wave front will be a plane wave, that is called a plane wave solution. So, e power I k x electromagnetic wave is an example of you have a plane wave, right. You have a solution like a sin k x or b cos k x, and a combination of these two, sine and cosine, e power I k x will be plane waves, right. The possible energy values in 3 dimensions, in 1 dimension I showed n square, in 3 dimensions will be n x, n y, n z, n z, n y, n z, and n x, n y, n z, all of them should be positive integers, right. A plane wave is parallel to the direction of propagation of the wave, and whose wave fronts are infinite parallel planes. These waves are plane and not spherical with increasing radius. So, this is a spherical wave front, this is a plane wave front, right. And let me now pass on to the example of electromagnetic wave, as I told you, is the one where you have a plane wave, right. It is an example of a plane wave. As I told you, the energy eigenvalue will be given as n square h bar square pi square by 2 m L square in the 1 dimensional case, but where you go to 3 dimensions, because solids are 3 dimensional objects, you know what a length, breadth and thickness, right. The solid, realistic solid has got 3 dimensions. So, when you go to 3 dimensional solid, n x, n y, n z, them will come, all of them are positive integers. Therefore, the integer space concept is important. Now, you should understand this energy is related to r square, and in some sense the integer space which I will show again, integer space is the momentum space or energy space. What I would like to tell you, this is an important point. The youngsters should know that I will ask the question, where do you come across this kind of integer space in your solid state physics or condensed matter physics? Can you tell me where exactly you come across a similar thing? When you discussed the lattice vibrations in Debye model, you have the same integer space. Here the question that you ask is, how many energy levels are there between the energy E and energy E plus dE, right? You have got here energy E, at the bottom you read E and E plus dE, and E and E plus dE corresponds to R and R plus dr. You have got R and R plus dr, and E and E plus dE comes the energy interval dE. E is the one energy level, E plus dE is another energy level. In this energy range dE, how many energy levels are there? That is the question that you pose. And in other words, you can ask how many momentum states are there between P and P plus dP, right? Okay. And in lattice vibrations in Debye model or in magnons, when you talk about phonons, you come across the Debye model. In the Debye model, you ask the question, how many frequencies, how many kinds of frequencies will be having, number of frequencies will be having between nu and nu plus d nu, right. Here you talk about energy of the electron, there you will be talking about the energy of the phonon, right. Therefore, you should know the connection in solid state physics or condensed matter physics between the various areas, right. I talk about electron dynamics, not phonon dynamics now, right. Then magnons, electron, phonon, magnon, the interconnection, the integer space concept is important, right. That is the reason why I am showing again what I showed in the last lecture, right. Therefore, every point in the diagram refers to a particular momentum or a particular energy, and the question that you ask in the spherical ring, in the annular ring with dr, right, how many points are there, and these are the points. Suppose you got 50 points, there are between E and E plus dE, there are 50 energy levels, is that right? In this annular ring, if there are 50 points, 1, 2, 3, 50 points are there, that means you have got 50 energy values, right. In this, what is meant by density of states? Of course, these things we did in the last lecture. The density of states, unfortunately in some of the books it is given as number of states per unit volume, which is wrong. The density of states means the variable is dE, energy, right. The number of energy levels in unit energy range, it is the density of states. Okay. Those things we saw in the last lecture, but now let us go to the periodic potential. Now, before we go to a periodic potential, let us see how the potential energy varies when an electron comes near the proton. In the hydrogen atom, what do you have? You have got only one electron and one proton, right. So, if the electron is coming from infinite distance to proton, how does the potential vary? Now, this is a question that I am asking, right. Now, this is a hydrogen atom, you have got a proton here, have the electron here. When this distance r is infinity, if the distance r is infinity, what will happen to potential? It is q square, q is the charge of the proton, minus q is the charge of the electron, right. So, your potential energy will be minus k times, it is a constant, times q square by r. When r is infinity, the denominator is infinity. So, the potential energy will be 0, right. So, when the electron is separated from a proton by a very large distance, the potential energy will be 0, right, almost 0. Okay. You see, when the potential energy will be 0, when the electron comes nearer to the proton, the value of the potential energy increases, right. The free electron, the electron is coming towards the proton. So, when the electron comes exactly near your electron cannot sit on the proton. If it sits on the proton, it will become infinity. See, it will become minus infinity. What is the meaning of minus sign? It is a bound state, right. The electron is bound to a proton, right. This potential energy diagram should be clearly understood. It is very simple. Now, in a solid, what do you have? You have got number of ions. How do you define a solid? A solid contains number of atoms. In a metal, how do you visualize a metal? I told you in the first lecture that a metal should be visualized as if it contains number of positive ions and free electrons. Therefore, I will show the periodic potential, right. I will show a number of diagrams to make things clear, and you find here you have ion here. Okay. I told you about sodium metal in the first lecture. So, in a sodium solid you will be left with positive ions, the outermost electron will become free electron. So, you are left with a number of ions, right, ion here, ion here, ion here, ion there, and so on, right. So, what is period? Because one ion is separated by another ion by a distance, that is, it is a period, right. Whatever that you have from, you take a particular ion, and from this particular ion you go through some distance, right. From this ion you go through some distance, the potential energy goes to this value, right. As I told you the earlier diagram, the potential will go to minus infinity. So, in the periodic potential problem, the potential energy varies periodically, right. This is what you observe now, right. Now, in the earlier diagram there is only one proton on one electron, the potential energy went like this. Now, it is a periodic arrangement of atoms or ions in solid. So, the potential energy will vary periodically. What do you mean by periodicity? Now, you go from this particular first ion, and then you go through 0.5 angstrom unit, you measure the potential energy, right. Then some other ion you go through again the same 0.5 angstrom, then the potential energy will be same, getting repeated. That is the reason why it is called periodic potential, right. Now, therefore, you go to, because it is a bound state. Now, this particular thing that I am showing is the realistic potential, this is how, but for the sake of simplicity, what you do is you remove them curved structures. The curves are made as in the form of rectangles, right, for imposing what are called, I will be talking about the boundary conditions and the periodicity conditions, the continuity conditions and periodicity conditions and so on. Now, therefore, the periodic potential is approximated to rectangles, right. What you have here now, the periodic potential, whatever that the curves are made a rectangle for the sake of simplicity, is that right. So, the problem will be getting simplified. It is easier to impose the continuity condition and the periodicity condition. Okay. Same thing, you got an ion here, as I told you the first picture, you got only one proton on one electron. Here you got a series of ions, and the potential energy will go to infinity when R is 0, and again the same thing is repeated, but in between the potential energy will be like this. It is made as equal to 0 or constant, right. For the sake of simplicity, it can be made as constant or 0. And what is meant by mathematically, what is periodic potential? V of x is equal to V of x plus N A, right. N is an integer, whatever energy, potential energy you observe at x will be the same thing repeated after n times the atoms, right, the atomic distance. The same value will be obtained, that is called the periodic potential. Now, came Felix Bloch and also a mathematician by name Flackfurt. So, Bloch got the Nobel Prize. This is called the Bloch's theorem. Now, Bloch's theorem or Bloch-Flackfurt's theorem is a very important theorem, because it only made us to understand the behavior of the electrons, how you get the conduction band, valence band, the origin of energy bands, the origin of energy gaps, they are understood because of the Bloch's theorem. The Bloch's theorem plays a very important role. The Schrodinger equation of an electron moving in a one dimensional lattice, again we go to one dimensional lattice because the problem can be simplified. That is what they did in 1920s, 30s with the lattice periodicity A is the lattice periodicity or x is the lattice periodicity, and that is the equation 1 refers to the one dimensional Schrodinger equation, right. Okay. And V of x is equal to V of x plus A, that is equal to V of x plus 2 A or V of x plus N A. N is an integer, it may be 1, 2, 3 and so on, right. Therefore, this is the Schrodinger equation, that is the equation 1, and you write here V of x equal to V of x plus A or n times A, right. V of x is periodic, the above equation can be rewritten in the form of a periodic differential equation. That is what Fluckford did. The mathematician Fluckford, he talked about periodic differential equation, where the function f of x will be equal to what? F of x plus a or f of x plus n a, right. The potential is v of x is equal to v of x plus a or x plus n a. Similarly, the function f of x will have a similar behavior. Okay. That is a periodic differential equation. Therefore, if you refer to the mathematics books, the Fluckford theorem, you have the f of x, the function will be equal to f of x plus a. You go through distance a, it is a periodic. Okay. Then f of x will be equal to f of x plus a, and psi of x, because the second order differential equation can be written in terms of solutions g of x and h of x. So, you write psi of x is equal to a constant c times g of x plus d times, it is again a constant, non vanishing constant, multiplied by h of x. Okay. And f of x is equal to f of x plus a. Similarly, g of x plus a and h of x plus a will also be solutions of equation 2. These solutions g of x plus a and h of x plus a can be expressed as linear combination of g x and h x. That is what we are going to do now. So, you write g of x plus a as equal to a times g x plus b times h x. Okay. Then h of x plus a, similarly you write a times g x plus b times h x, right. Then substituting the above in 3, we get psi of x plus a is c times g multiplied by x plus a plus d times h of x plus a. That will be equal to c times a 1 g of x plus b 1 h of x plus d times a 2 g of x plus b 2 h of x. Therefore, psi of x plus a will be getting reduced to taking them constant c and d together. You have g of x is common, h of x is common, pulling out g of x and h of x, that will become c a 1 plus d a 2 multiplied by g of x plus c b 1 plus d b 2 into h x. The same is rewritten in a different form, right. Psi of x plus a is given in this form, that is equation 4. Okay. They are simple mathematics, right. Therefore, you pass on to, since psi of x plus a can be expressed in the form psi of x plus a lambda times psi of x, because your psi of x plus a is same as psi of x excepting a constant lambda. So, lambda multiplied by g of c times g of x plus d times h of x, where lambda is a constant, right. Comparing equation 4 and 5 and equating the coefficients of g of x and h of x, we are led to the following equations: c a 1 plus d a 2, these are all simple mathematics. G of x will be lambda times c into g of x, and c b 1 plus d b 2 h of x is equal to lambda times d into h of x, or you can write this as c times a 1 minus lambda, okay, into g of x. You are taking this to the left hand side, plus d times a 2 into g of x, that is equal to 0. Okay. Then a similar equation you have got c b 1 h x plus d times b 2 minus lambda into h of x is equal to 0. In order that g of x and h of x do not become 0, as you get in regular mathematics, the constant coefficients c a 1 minus lambda plus d a 2 should be equal to 0, and c b 1 plus d into b 2 minus lambda should be equal to 0, or the determinant that you will have. The solution, so the above equations are contained by making the determinant of the constant coefficients to become 0. A 1 minus lambda, A 2, this is the determinant, right, and B 1 B 2 minus lambda should be equal to 0, the equation 6. Now, this multiply A 1 minus lambda into B 2 minus lambda, right, minus A 2 B 1. Okay. that is otherwise lambda square minus a 2 plus b 2 into lambda plus a 1 into b 2 minus a 2 into b 1 is equal to 0. The same is written in this form, right. Determinant upon multiply this 2 terms along the diagonal, then subtract the 2 terms along this diagonal, right. Okay. So, the above quadratic equation will have two solutions, lambda 1, lambda 2. If these roots lambda 1, lambda 2 are taken as lambda 1 is e power I k 1 a and lambda 2 is e power I k 2 a, and also we will define u 1 of x is and u 2 of x as, let us define u 1 of x is equal to e power I k 1 a psi of x, and the u 2 of a is e to the power I k 2 into x into psi of x. Now, the e power I k that you are getting now is the actually the plane wave, right, is a plane wave, that is equation 8. And so, Bloch's theorem says, I told you the plane wave, if you have got only this particular thing, is a plane wave, right. Here when you have a periodic potential, or the Bloch's theorem states that psi k x is not simply e power I k x. Simply e power I k x is a plane wave. The plane wave modulated by a factor u k of x, that is the Bloch's theorem. The solution of the periodic differential equation, these are mathematics, right. u 1 of x plus a is equal to e power minus I k 1, all these things to the power of x plus a, psi of x plus a is equal to e to the power of minus I k 2 x plus a into lambda 1 psi of x, and the same thing e power minus I k 1 x plus a e power I k 2 a into psi of x is equal to e power minus I k 1 x psi x is equal to u 1 of x. This shows that u 1 of x is periodic. Similarly, u 2 of x also is periodic with the period a. A is the period, means a is the interionic or interatomic. The equation 8 is rewritten for the electron with momentum vector a. K is the momentum vector. You write the solution of the periodic differential equation we wrote, d square psi by dx square plus 2 m by h bar square into e minus v x into psi is equal to 0, but the potential energy V of x is V of x plus N A. If you have got a periodic differential equation of that kind, the solution according to Bloch's theorem is psi k of x is e power I k x into u k of x. This is a very important relation, and let me go back to this particular thing. These two are important. What do you find here? This is the ultimate relation that you get from this is the Bloch's theorem. The Bloch's theorem shows the wave function of the electron moving in a periodic potential, moving in a solid where the ions are arranged in a periodic manner. The wave function will have this form e power I k x multiplied by u k of x. On the other hand, if the periodicity is forgotten, if you don't you consider the electron to move in a constant potential, right. I told you the wave function of the electron moving in a constant potential as the form e power simply I k x. U k of x is missing, right. That is the difference. This is the Bloch's theorem. Okay. This one is a plane wave. Okay. This one is plane wave. The electromagnetic wave is the example of a plane wave. Okay. Now, the important thing is this solution will be made use of in the time to come. In the lectures to come, I will be making use of this solution, because you are dealing with a solid or a metal where the ions are periodically arranged, and the potential cannot be treated as a constant. Wherever when the electron is very near the nucleus or far away from the nucleus, the irrespective distance, the potential cannot be same, right. Assuming the potential will be same, the first approximation, the actual thing will be different. Therefore, you have the this kind of thing in a 3 dimensions. It will become it will take a form of UKF, or the details of which we will see in the summary goes as follows. There are two simple things. You write the energy of the electron in a constant potential, that is on the upper side. Constant potential eigen function is given like this, but on the other hand, according to Bloch's theorem, the eigen function looks like this. I will not talk about eigenvalue. The eigenvalue in the lectures to come, we will see the eigenvalue is not going to be simply E and k related by a free electron parabola. We will continue the rest of the things in the lectures to come. Thank you.